Hello and welcome to this week 9 class on graphic engineering TA session. Since it's 2 minutes to 7, I'll wait for 5 more minutes to see people join in and then I'll get started with today's content. So since it's 7:05 already, so I'll start with today's class. Hope more people will join in as time goes. So welcome to this week 9 class on traffic engineering TS session. So today I'll be discussing mainly about the car following theory and the traffic simulation that were discussed in this week's content, and I'll be solving some similar problems that you'll find in assignment 9. So I'll get started with today's discussion. I'll turn off my video and share my screen. Okay, so hope my screen is visible. So let me get started with the contents. So to give you an overview of the topics that were covered in this week's lectures. So first is car following theory. And within that, you had different uh, features that were kind of there and theories as well. So one is space headway. Next was pipes theory, pipes and force theories. Next, there is this GM theory, which is the General Motors theory. Then there was some discussion on traffic stability. So, next was Weidman car following models. The discussion were not in detail for this, and it's not required as such for this course. But anyway, whatever was there in the assignments, I'll be discussing those things today. Next was the traffic simulation part. So within that, we have again different things. One is studying a system, then classification of simulation models, next was principles of traffic flow modeling. The last one was traffic microsimulation. So all these things were discussed in detail in this week's content, and I found this week's content was much easier to follow because there is very little maths involved in it. It's more like a general discussion that were presented. So let me get started with assignment problems directly. Similar problems, mind you, not the exact numbers that you will find in the assignment. So let me see. Okay, so this is the overview of today's discussion. As I was mentioning, now I'll be solving one problem. So that you will find a similar problem in the assignment. So let me get started with that. So I'll give you the problem data. You can take some time and start solving, and then I'll give you the solution as well. So first, so the data is you have a leading vehicle. The leading vehicle and following vehicle are traveling with a speed of 16 meters per second and space headway of 25 meters at t equals 0 seconds. Lead vehicle accelerates. The problem data is different from what you'll find in the assignment. Accelerates by 1.2 meter per second square for 1 second. Next is the simulated behavior of the following vehicle is as per the first generation General Motors. So different generations were discussed in this week's video. It's car following model. So the equation you will know exactly. It's the acceleration at t plus delta t. It's related to the speed differences of the lead and the following vehicle at t multiplied by some factor which is alpha, which is also called as the sensitivity coefficient. So now I'll write assume sensitivity coefficient 0.5 per second. So the unit will be per second for this first generation model. Reaction time, which is delta t, is equal to 1 second, and update interval of 0.5 seconds. So now the first question that is asked is, what is the speed of the lead vehicle, so meter per second, at t equals to 2 seconds. So this is the question. So I'll keep it for some time here so that you can take the screenshot and then you can start solving it. And maybe you can tell me the answer and then I'll start solving the problems. So yeah, maybe a couple of minutes to see if anyone else joins as well. Okay, so let me start to solve this problem. In another slide, I'll start to solve this. So hopefully you have taken the photo of this problem data. Okay, so let's write the solution here. So what I'll do, I'll create a table which updates this different terms like the speed, acceleration, those things at every 0.5 second intervals for both the lead and the following vehicle. So I'll need two columns and 6 rows. Okay, so let's start to populate this. So this is t in seconds. So next we will have x1 double dot, which is the lead vehicle's acceleration. So x1. So I'll write it as acceleration of lead vehicle. This is in meter per second square. Next you have the speed of the lead vehicle, which is x1 dot This is in meter per second. Next, we will have position of the x1 position, which is x1 of the lead vehicle. This is in meters. Next, we will have the acceleration of the following vehicle. This is again x2 double dot. This is again in meter per second square. Then you will have x2 dot, which is speed of the following vehicle. This is in meter per second. Then you have x2, which is the position of the following vehicle. This is m, so this position means x2. Then you have the relative velocity or relative speed, we can call it, in meter per second, which is again nothing but this x1 dot. So this dot of x1 minus the dot of x2. And finally, you will have the difference between the positions, which is x1 minus x2. So this is in meters. So these are the things that you will require, and this updates. So if you go back to the problem, so it starts at t equals 0 when the lead vehicle starts accelerating for 1 second. And the simulated behavior, you have to find at every, say, 0.5 second interval, but you need it for the speed of the lead vehicle at t equals to 2 seconds. So we have to populate this table to 2 seconds. So this is 0. For the next one, it will be 0.5, then it's 1, then it's 1.5, and then it's 2. Now, acceleration of the lead vehicle, it will come from the problem data itself. So this is 1.2 meter per second square for 1 second. So this will be at t equals to 0 it starts. So this is 1.2. This is again 1.2, and after 1 second is over, there is no acceleration. So these will be 0. Now, there is some information about, I think, speed of the lead vehicle, which is, so both are traveling with a speed of 16 meter per second to begin with. And the speed headway is given as, sorry, the space headway is given as 25 meter. So this will be 16. So next ones we have to update because there is some acceleration that is happening. So the speed won't be constant and subsequent steps. Position of the leading vehicle, so it's have a x1, so that will be 25 meter head start it will have over the other vehicle. So this will be 25. And the other ones you have to update based on the other values. Next is the acceleration on the following vehicle, right? So this again, you have to update it, but to begin with, it will be 0 and it will react based on how the leading vehicle goes. So that's one thing. And so let's maybe bother about the other part later because that's related to the I think this model, this GM model. But for the first problem, let's focus on this one. What is the speed of the linked vehicle at t equals to 2 seconds? So for that, what you have to do is you have to keep updating the speed of this lead vehicle based on the simple formula, which is v equals u plus at. And your t is 0.5 seconds duration, u is the initial speed, and your updated speed after, say, 0.5 seconds will be based on the acceleration that you have. So this is nothing but 16 plus, so that's u plus at. A is 0.2 times 0.5, which gives you a value of 16.6. Similarly, here also we will have 16.6 plus 1.2 times 0.5, so which gives you 0.6 you are adding, so that's 17.2. Similarly, for the other ones, it will be 17.2 because now you have zero acceleration, so there won't be any second term, so this will remain as 17.2. And for the last one as well, it will be 17.2, right? So your answer will be for the first problem is 17.2 meter per second because that was what it's asked in this problem. So this part was very simple. So let me write down maybe the second problem and I'll populate the table after that. So the second problem is what is the distance headway, which is x1 minus x2 in meters between the lead and the following vehicle at t equals to 2 seconds. So basically what you have to do now, you have to find this one at the end of t equals to 2. So that's a challenge now. So it's essentially now you must be filling this table up, so that's your goal now. So let's do this one by one. The first one is this updation of this position of the lead vehicle. And for that you have another formula which is S equals ut plus half at square. So that ut plus half at square is the term that will add up with this 25 whatever you have at this point of time. So this is 25 plus u is so at the start of this at 0, u is 16. So that's u times 0.5, that's ut plus half times a is your 1.2 a. Then you have t square means 0.5 times 0.5. So this will be your updated position. Okay, sorry, maybe just to make this table. Okay, so this, let me calculate it and see what's the updated value. So this is 25 plus 16 times 0.5, so it's 33. We have 5, 2 times 5 times 0.5. Okay, comes out to be 33.15, which I'll take it as say 33.2. Or let me just put it as 1.5. Okay. It's fine. Next is again you have to do this update. So for that, what you will have to do, it's the same thing. So this is 33.2 plus u is now your 16.6. So that's u times t plus half. A is again 1.2 and then you have t square. Okay, so this comes out to be, let's check. So it will be 41.6. If you take this one as 33.15, so I'm rounding it off to say 1 decimal place. So that's 41.6. Next is the updation here. Okay, let me see if I can increase the bit. Yeah, next is again, you don't have any AT squared term here, so it's whatever you had 41.6 times U times T. So this is 17.2 times 0.5. So I'll directly write it because now you should be able to know how to do this calculation. So it's coming out to be, I think, 50.2. And for the last one again, it's the similar calculation. It's 50.2 plus U times again T. So that's 17.2 times 0.5. So it's, I think, 58.8. So we have updated x1. Now, if we can update x2 somehow, then we'll know exactly how this difference looks like. So right now, the calculation for, okay, so the calculation for x1 is done. Now we have to do the calculations for x2s. So for the following vehicle, there are some information that are given. So one is that it's traveling with a speed of 16 meter per second, and the space headway is given. So x2, so this is 0 to begin with. Speed of the following vehicle to start with, it is 16. There is no acceleration as such, so this is 0. Now, so this x1 plus x2, it's here it's, this is x1 dot minus x2 dot, which is speed, this one minus this one. So this relative speed is 0, and this, okay, sorry. And this one is x1 minus x2, which is 25. So that is fine. So the first row is filled now. Now we have to update the acceleration of the following vehicle, and that we have to do using the term that you have, the General Motors first car following model. So that's now the delta t is given as 1 second. So that's the reaction time. So you can only have an updation of this acceleration after that only. So till 1 second, you won't be having any acceleration. So this portion remains 0 till t equals to 1 seconds, because that's your reaction time. And the speed will remain as constant because it's the same formula, right? So this will be same. Position will be just 16 times 0.5. So this will be 8. This will be plus 8 plus 8. So that would be again 16. So hope this part is easy. Now we have to fill this one. So this is the relative speed. So this is 0.6 here. This is 1.2. And this is the positional difference, which is 33.2 minus 8, which is 25.2. And for this one, it is 41.6 minus 16, which is 25.6. Okay, so these things are now filled up. So what we have to next we have to do is fill the acceleration for this 1.5 seconds. So here your t will be 0.5 and your delta t will be 1. And what you have to do, you have to do alpha times. So your alpha is this sensitivity coefficient is given as 0.5. So this is nothing but alpha times. So then you have xn dot, which is at t, means at 0.5. So this is 16.6 minus this relative speed, which is x2 dot, which is here it is 16. So it's the difference, it's already written, it's 0.6. So we can directly apply it here. So let me write down the entire thing. So this comes out to be, I think, 0.3. So that's your acceleration. Okay, so this is visible for now. So the calculation is clear, right? I'll just write it as 0.3. Next, what you have to do, you have to find the speed, and the speed you can again find using that v equals u plus at formula. So here what you can do, so your u is this 16, your acceleration was 0 previously, so this will remain as 16. Position will be, so from 1 to 1.5, so s equals ut plus half at square, a is 0, so it's whatever you had plus ut, so this is 16, and then you have the speed as 16 times 0.5, so this will be 24. The relative speed between these would be 1.2, and the difference of positions would be 26.2. So this is the 50.2 minus 24. So we have to now just fill the last row for here. And for that, what you have to do is a simple technique, which is, again, you have to update through this GM model to get the acceleration and just fill the entire thing. So now, you know your alpha is 0.5 and it's 2 seconds. So your t is 1. So at t, the difference was 1.2 seconds. So that's x1 dot minus x2 dot. So it's alpha 0.5 times 1.2. So this will come out to be 0.6. The speed will be whatever you had, 16 plus at. So this is 0.3 times 0.5, which is basically we'll be adding 0.15, which I can round it up to write 16.1. Position is whatever you had, 24 plus ut plus half at squared. So your u is 16, t is 0.5, so that's 8 plus half times a is your 0.3. So it's 24 plus u is 16, 0.5 plus half a is 0.3, and then we have this square, t square. So I'll just calculate and write the final value here. So this will give you 24 plus 16 plus 0.5 plus 0.5 times 0.3 times 0.5 times 0.5. Okay, so it will be, I think, 32.03 something. So if I round it off, I think I'll be getting around 32.1. Yeah. So let's write it down as 32.1. And then it's just the difference. So your positional, first is your speed difference, which is 1. So 17.2 minus 16.2. So it's around 1. And the other one is 58.8 minus 32.1. So that would be around 26.7. So that's your final answer. There could be some rounding off issues, but it should be close to this because I have taken till 1 decimal only. So this one was asked. So this is your one of the answers. Second, this one was asked, so this is another answer for you. Now let's see if any more questions were asked here. Next is the third one. So what is the value of acceleration for the following vehicle at t equals 2 seconds? So again, if you go back to this table, if you fill this table, then it's very easy. So this one is your answer. And I think there was one more. So what is the speed of the following vehicle at t equals 2 seconds? So again, it's simple. If you go back to this table, here is your answer. Okay, so it's just filling up this table and you will get all the answers from here. So I think a similar question were asked in the assignment where instead of acceleration, you have a deceleration. So the signs will be reversed. It's A is negative, we can think of it that way. And you have to update the table the way I have shown. So hope this part is clear. If any doubts regarding this question, you can ask. Otherwise, I'll move to the next uh, problems or the next maybe the questions that we'll be getting in the assignments. I'll pause for a couple of minutes and then I'll get started. Let me check something in the chat. Okay. So I hope that problem is clear to you. So you can go through this later as well and check for the solutions. So maybe let's get into the some of the other discussions in this from this week's I think content. As I have mentioned before, it's very simple than the discussions that you will find in the previous weeks. So let's maybe I'll write a couple of questions and you can say what would be the answer to this. So state true or false. So this one is as per the third generation CF it's CF, I think there is a typo. Okay. Write it as GM model. Dimension of sensitivity constant is, or unit you can say, instead of dimension, is meter per second square. Is it true or false? So this is sensitivity constant is alpha naught, or alpha c. That's one of the problem. Next is space headway is inversely proportional to time headway. Next is traffic density is directly proportional to average space headway. Next is larger the spacing between the vehicles, higher is the level of service. And the fifth one is space headway lower than critical spacing results in a very high LOS. Okay, so let's solve this one by one and try to relate it to the problem or the topics that were discussed in the weekly content. So the first one is related to the third generation general motors model. So let me quickly check exactly where this comes in the lecture. Yeah, so I think it's in the F2 lecture, where you'll find this different generations of GM theories and their models. So here what you will have is for the second generation, sorry, it's the third generation that is asked. So the expression is alpha term is nothing but alpha naught divided by xnt minus xn plus 1t. So in slide, I think 32, you will find this. Now, this is multiplied with the relative speed to get the acceleration. So you need to find the unit of alpha naught. So unit of alpha naught is basically what you have to do. In the left hand side, you have meter per second square, which is the acceleration. Then if you divide it by speed, which is the relative speed term, so that's second per meter. So if that goes to the other side, and then we have a term related to the what you call this, the space headway. So that's meter. So this meter and meter will cancel out, and it's meter per second square times a second. So it will be meter per second. So it will be the unit of speed. So this will be false. So I hope this will be clear to you. Next is space headway is inversely proportional to time headway. Is that true? Let's check. Space headway is basically related to the physical length of the vehicle as well as the gap between the vehicles. So the time headway is maybe if you can relate it with the gaps as well, but the length of the vehicle turn is always be there. So cannot say it's inversely proportional or proportional or any kind of relationship like that. So this will be false. Okay. So did anyone answer anything in the chat? Next is this traffic density is directly proportional to average space headway. So this is again, let me check if it's there somewhere in the. Yeah, so if average space headway is known, the traffic density you can find out using a formula which is k equals say 1000 by d. You have to keep in mind the units of what you put in d and k. But anyway, with increasing value of space headway, which is d, your traffic density will go down. So that means it's not directly proportional, it's inversely proportional. So this will be false as well. So next is related to the spacing and the level of service. I think this was also discussed. So spacing between vehicles influences the capacity of roadway as well as the LOS. Now, as spacing decreases, drivers have to pay more attention and may have to reduce speeds, resulting in lower LOS. So that's one thing, but increased productivity until spacing remains more than it's critical, so that's fine. And if spacing is minimum, vehicles are stopped, and that's the lowest LOS possible. But when you have larger the spacing between the vehicles, higher is the level of service. So this statement is not always necessarily true. So I think this should be false. Let's see if anyone answered it in the chat. Is it true? Okay, but should not be the case. Now, if the spacing increases infinitely, so it's like vehicles are very far apart from each other. It's not like you are increasing the level of service. You have a capacity which you are not utilizing. So your V by C ratio will be very less. So it's not always true. So this statement is actually will be false. And the last one, space headway lower than critical spacing results in a very high LOS, which is not true as well. So because that reduces LOS, so this will be false as well. So I hope this will be clear to you. See if the answers are fine. Yeah, yeah, all of them are false here actually. Yeah, none of them true. Okay, so let's see what else we can solve. So the next slide, I'll put some more questions and then I'll again be discussing this. All right, so here what you have is again state true or false. So first is underline logic of traffic microsimulation models is inherently deterministic. That's one. Next is as per General Motors are following model. The lead vehicle decelerates, then at time t, the following vehicle at time delta t, you can write it as delta t. So accelerates. Okay. Next is okay. First, let's solve this two, and then I'll move to the next one. So the first one is from the traffic microsimulation part. So do you have any answers to this? I'll wait for a couple of minutes to see. Okay, so the first one, okay, so let's see. First one is on traffic microsimulation, and it's not true. It's the underlying logic is not deterministic. There are a lot of stochastic components that goes into it. So actually, it's inherently stochastic. So that's why it's false. And for the General Motors car following model, if the lead vehicle at time t decelerates, then the following vehicle at time delta t can never actually accelerate, right? So actually, let's frame this question as, so this is confusing. It's at time t plus delta t because there will be some reaction time, which is delta t, that is involved. So if you look at the expression in General Motors model, so your alpha is the sensitivity parameter, which is positive, and you can check for the acceleration of the, say, leading vehicle, and then you can relate it with the relative speeds of the leader and the follower. Sorry, the acceleration of the following vehicle is you can relate it with the relative speed of the leader and the follower. So it happens that the lead vehicle decelerates, the follower vehicle has to decelerate as well. So its acceleration is not true. So this is false as well. So yeah, I think this should be clear. Next, let's now move to the next problem. So let's take here. So which of the following is true with respect to Forbes car following theory? So let's now write down the statement. First is minimum safe distance headway decreases linearly with speed Next, minimum safe time headway continuously increases with speed. Then you have at lower and higher speeds, there is considerable similarity in a pattern similar to pipes model, and then we have h mil is the difference between the reaction time and the time required for the lead vehicle to traverse a distance equivalent to its length. See if which of the statements are true. So this force per car following model theory, I think, was discussed in the initial stages along with Pipes model. So let me just open up that part and confirm what should be the correct answers. So meanwhile, you can answer this in the chat as well. So in the Forbes car following theory, so they considered this reaction time needed for the following vehicle to perceive the need to, say, decelerate and apply the brakes. So this minimum safe distance headway decreases linearly with speed. So that's one thing. Let's check. Okay, we have an answer. Let's check. One is true. Let's see. Yeah. So that looks like to be correct answer. Distance that way. So there is one plot, I think, that's shown. So that's speed in miles per hour, as well as then the safe distance that way, that's in feet. And the relationship looks to be linear in nature. But let me just confirm, is it linear or not? So in Pipe's theory, that's true, that your minimum safe space headway increases linearly with speed. And here also, the trend is like if speed increases, it should increase. So I think this statement with decreases linearly, that is, I think, false. Linearly is obviously, I think that's true, but this increase and decrease thing, I think that is what's confusing. So that should be false. One should be false. Okay, 2 I'll check, but one is false. It's not true. Because the statement should be minimum safe distance headway increases linearly. Okay, so now minimum safe time headway continuously decreases with speed. Let's check this. So minimum time headway is the one which is, I think, h min, which is, so if you increase speed, so that's correct. It will keep on decreasing because the second term that is there will be reducing that term. So 2 will be true. So that's correct answer. Let's check if anyone else answered everything. Okay, so we are seeing B is true. Yeah. Let's check if all others are false or not. So at lower and higher speeds, there is considerable similarity in a pattern similar to Pipe's model. So that's not the case. I think let's confirm. So when you have low and high speeds, considerable similarity in pattern similar to Pipe's model. So I think in the slides also it's written in the mid speed range, there is a close agreement between the force model and the field study. And at lower and higher speed, there is considerable difference in a pattern similar to Pipe's model. So this is false. And finally, h min is the difference between reaction time and the time required for the link vehicle to traverse the distance equivalent to its speed. This statement is also false because the definition of h min is something else. I think that's given. Check where is it's written. H min is the minimum safe speed headway. Sorry, h min is the minimum time headway, and this is equal to the reaction time and the required for the vehicle. Okay, I think just okay, so it's not the difference, it's actually equal to the addition of those 2 terms. So that's false. So yeah, that's about this question. I think that should be clear. Let's move to the next one. Let's see what's there after this. Okay, so solve some more of this in the next slide. So in state, yes. Okay, so state true or false. So this is about the model, I think, validation, those things. Okay, so this one is model validation. It's the process of modifying the default microsimulation parameters so that the model replicates the observed traffic conditions as accurately as possible. Okay, so that's one. Next is yeah, in the traffic microsimulation, traffic demand is typically entered as individual vehicle movements rather than uh, rather than as a deterministic number. Okay, so what would be the answers to this? Can anyone tell me? Then I'll move to the next question in the next slide. Okay, in this context, I think I'll just add a couple of more true or false here as well because it's related to traffic microsimulation. Traffic microsimulation models help in representing complex traffic systems. And the next one is the state of traffic, the traffic signal indication indicates a discrete model. Discrete simulation model. So let's see what would be the answers to this. Q1 and Q2 false, Q3 true, Q4 A. What is A? True or false? Okay, so what he has said, I think mostly are correct. So the first one is model validation is the process. Okay, so yeah, 3, 4 is true. Okay, correct. Yeah, I think all of them are correct. So yeah, it's not model validation, right? It's the calibration that kind of modifies those parameters. So this is false. And it's actually this in traffic microsimulation, the traffic demand is given as a deterministic number. So that was discussed in the class itself. So this is also false. And this is true that it helps in representing complex traffic systems. This is in general question. And this indicates a discrete simulation model. That is true because this traffic signal changes abruptly and this happens instantaneously at the point. So it's not any continuity that's happening. So there is some jump that is happening at that point of time. So that state change is happening. So that's why it's a discrete simulation model. So this is also true. Okay, so now let me go into the next problem. So let's see how we'll do. Yeah, next one is again something related to the general methods model. So, so which of the following state or values like state true or false with respect to general methods are following rule. So the first one is as per the second generation model, high sensitivity value is alpha 1 should be employed when vehicles are far apart. Next is third generation model takes into account distance headway between and following inputs. Next is fourth generation model is developed to improve the sensitivity term by introducing the speed of the leading vehicle. The fourth one, in a generalized, this GN model, if distance headway exponent is 1 and speed exponent is 0, it will result in third generation GN. Okay, so let's answer this. These are again pretty straightforward from the class itself. So I'll wait for a couple of minutes. You can answer, then I'll give you the correct answers. So let's see. Answers to this one. Okay, the first one is false because this is true when the vehicles are close to each other, not far apart. So it's like you have two terms, alpha 1 and alpha 2. When alpha 1 is employed, then it's a high sensitivity value, and when vehicles are close to each other, alpha 2 is applied when the vehicles are far apart. So that's for a kind of a lower sensitivity value. So that's why it's false. So the next one is true because you have that distance headway expression within that. So that's xn plus 1t minus xn t. So that's there in the third generation model. So this is true. Then you have in fourth generation model, it's developed to improve sensitivity term by introducing the speed of the leading vehicle. This is false because the speed of the following vehicle is introduced. And finally, this one is also true because distance exponent is, I think, so what is that was L. Yeah, L is 1 and M is 0. M is the speed exponent. If you plug those in the fifth generation model or the generalized model, then you will get back the third generation GM model. So this is true. Okay, so that answers this question. Next, let's get to the next problem. This is see what the things likes to run. So next is I think this traffic stability thing. One question related to that. So state true or false with respect to stable behavior in car following. Okay, so let's see. This is first one is over response. Is high reaction time. Low sensitivity. Fourth one is attentive driver. What are the correct answers to this? Again, it's very simple. The stable behavior was described in the class. Let's check. Yeah, both stable and unstable behaviors were discussed, and the differences are there, and some connection issues today. I think, yeah, I dropped off the call, so maybe share the screen again. Hope it's visible again. So here you have to state again true or false with respect to stable behavior in car following theory. So the unstable and stable behaviors were discussed in the class. So in unstable behavior, driver over response, and there are high reaction times, and the sensitivity is also high. But that's not the case in stable behavior. So the first two will be false. Then this is true that it's low sensitivity drivers and low reaction times, and drivers are more attentive in this case. So both of these are true. Okay, so that answers this question. Let's see what else are remaining here. So again, there is another question related to this traffic stability. So let's discuss that in the next one. So here, again, with respect to traffic stability, the value of C equals 0.6 indicates that, let's write this first one, no oscillation would occur between lead and following vehicle. Then there could be increasing oscillation between lead and following vehicle. Third one is none of the following vehicle will collide considering a line of car following vehicles. Two or more of the following vehicles may eventually collide considering a line of car following vehicles. So what would be the answer to this? Let's check. That is not what I just did. Sharing video. Okay, so this is the problem that I have. So it's related to traffic stability and the C value is given. Now you have to answer this. So let's see what would be the correct answer. So the C is nothing but it depends on two terms. One is the number of vehicles in the car following process and also the reaction time. So and the sensitivity term. So C is actually the product of reaction time and the sensitivity term alpha. Now there are two types of stability I think that were discussed. One is the local stability. So if in case of local stability, there is something, there are only two vehicles that are involved and the lead and the following vehicles. So I think the first one is related to the local stability and the next two ones are I think related to a line of vehicles which is asymptotic stability. So for local stability, if your C value is within 0.37 and 1.57, which is within, this is 0.6 value that is given. So that means the following vehicle oscillates, but over time, oscillation decreases and vehicle becomes stable. So this is false because there will be some oscillation and there is decreasing oscillation. Over time, this becomes stable. So this is also false. Now, in terms of this asymptotic asymptotic stability, what happens is that when C is greater than 0.5, that means you have the 0.6 value here, two or more of the following vehicles would have eventually collided. So the thing is that here the C, the third one is also false. So there's two or more of the following vehicles would eventually have collided. This one will be the true one. So your answer is 4. So it was simple from the slides itself. Yeah, so my screen is still visible. Internet is unstable here today for some reason. Okay, so let me check which of the things are still remaining. So there are a couple of questions related to matching type. So maybe I'll just solve those. Then I'll check there is something else to me. Okay, so some matching type problem. We have to match column X with column Y. So there is some information given in both the columns. So let's actually create table of 2 columns, 5 rows. So this is column X. This is column Y. So one is free driving. Second is approaching. Third is following. Fourth is braking. Column Y we have driver lies, medium, high, deceleration rates. is driver maintains his desired speed. Drivers keeps safety distance constant. D is driver adapt adapts to a lower speed of the preceding vehicle. Okay, so what would be the answer to this? See, so, okay, it's very simple actually from the problem itself. Yeah, free driving, no influence of preceding vehicle. That's true, but here, yeah, correct. Driver should maintain his desired speed, so that's free driving. Approaching means driver have to adapt to a lower speed of the preceding vehicle. This would be D. Following means drivers keep safety distance constant. So that's C. And your fourth one, braking means driver applies medium to high deceleration rates. So that was simple. Okay, so let's solve one more of this. Then I think I have mostly covered the questions, but I'll check if there is something that's left. So there is another matching problem. So yeah, sure. Yeah. This match the different principles of traffic flow modeling. So again, it would be very simple. Mhm. So, so this is column X, column Y. One is microscopic, A is individual vehicles. Two is actually let's call this as macroscopic. Two is microscopic. This is vehicles Stacked in platoons. 3 is mesoscopic. This is aggregated pointers. So again, it's very simple from the slides itself. So let's answer this. This is pretty simple nuances to this. Yeah, macroscopic is the aggregated point of view. So that's very simple, should be seen. Then two, microscopic is dealing with individual vehicles, so that's 8. And the third one is mesoscopic, where vehicles are packed in platoons. That's B. So that's the correct answer. Okay, so now let me check this year's assignment problems. Something that's left out. So the first question, I think it's related to what I discussed. But instead of acceleration, you are given deceleration, so you have to work it out yourself. And yeah, everything is asked at 2 seconds. So the table will be similar. But the fourth problem, I think it's related to this traffic stability and oscillations and so on. Yeah, so I think that you have to answer yourself as well. Then, okay, let me just, this is, fifth one is easy, I think. Sixth one is again, seven, okay, any doubts from the assignment problems? I think I've mostly covered. If you want me to discuss any specific problem, but I won't be giving you the exact answers. You can ask if you have any like doubts in solving. Since we have some time, maybe I'll just solve one or two matching problems. So let's work it out. Scholar X. First CF model, like the car following model, according to this general models. Second one is third CF model. Third one is this suppose it's CF model. N equals 1, N equals 0, N equals 1, N equals 1, C equals N equals 0, N equals. So it would be the answer to this. It's very simple. It's directly from the assignment, so you should answer this. There's a new answer in the chat. It's directly from the slides as well. So it should not be too difficult. Answers. Go through the slides, you'll be able to answer this. But for first CF model, there is no L and M involved, so this will be C. Or the second one, which is the third CF model. Yeah, answer 1A, 2B, 3C. That's not the correct answer. Go through the slides because this is direct question from the assignment. If you struggle here, then that's a major problem, right? Because it's clearly written in the slides. So first one, L and M doesn't have any term involved, so those exponents are zeros. For the third one of them are present, so L is 1 and M is 0. So for 2, it's A. For the third one, which is the 4CF model, both L and M are present, so this will be B. You should be at least able to answer this because it's there in the slides. So maybe one more before I wrap up today's class. So let's see this mail. So next, it's again similar to this another matching problem. This is column X, column Y. First generation model, this later. So second generation model. This is third generation model. This is fourth generation model. This generalizes the sensitivity by introducing space headway exponent, speed exponent. Yes, sensitivity is a function of constant alpha 0 and space headway. C is constant sensitivity term. D is sensitivity at two different states. So let's answer this. This is again very easy from the slides itself. Let's check 1C, 2D, 3B, 4A. 1C, 2D. Yeah, I think that's correct. Yeah, you're right. So for the first generation model, there is only constant sensitivity term. Second generation model, we have two different states, so that alpha 1 and alpha 2. For the third generation model, so it's a function of alpha naught and space headway, so this will be B. And the fifth generation model generalizes everything, so that would be A. Okay, so I think that's mostly the discussion for this week. We have covered most of the things. The rest of the questions I think we should be able to answer. We go through the slides and also the discussion in this previous sessions. So yeah, if you have any specific doubts, you can ask now or post later in the discussion forum. So with that, I'll stop this discussion for today. If you have any questions, ask now. Otherwise, feel free to leave the meeting. Q6, is it? Let's check what is there in Q6. Following vehicle has following characteristics. It's for the first GM car following model. Sensitivity coefficient is alpha given. Reaction time is given 1.5 seconds. If there is change in relative speed of lead and following vehicle, which of the following statement is true? Okay. So first of all, you have to calculate C value. So that's pretty straightforward. So you have to multiply this with this. So that's I think 0.75. So automatically this option D is wrong, right? So now you have to check for this oscillations and all. So your C value is I think 0.75. And when you have that, so let me just check the ranges. One is for local stability, and so here there is change in relative speed of lead and following vehicles. So I think this comes under the other condition. So yeah, so no, that's the first condition because uh, there is only two vehicles that are involved. So your C value is 0.75 means you have to check whether it's damped oscillation or no oscillation or the increasing oscillation. So that's under local stability. So I'm not giving you the direct answer. It's C is 0.75 and then work it out whatever. I hope that answers your question. It's directly from the slide. Any doubts? Else I'll close the session. But So if no more questions, I'm closing the session. So see you all next week with the content of week 10 and the assignment 10.